So here we have a question where there's a box being pulled in 4 different directions by 4 different forces. We want to find the total force acting on this box. And in doing that, we can also find the direction that the box moves in. So we can't approach this question like one of our previous questions. We have this question, or this vector here, force 1 and force 2, which are fine to work with. We can add those together. But the problem is F3 and F4 aren't perpendicular to the other ones. So we have to break them down a little bit before we can actually add them together. And that's what this lesson is about, the component method. Components refer to the x and the y parts of a vector. So if we look at, for example, vector 1, or F1, let's just draw that one like that. It looks like that. It has a magnitude of 104 newtons to the east. Right? And what we're going to do actually, before we do this question, we should define what our positive directions are. So I'm actually going to say that right is going to be positive and up is going to be positive. So right is positive in the x direction, up is positive in the y direction. And that'll just help keep everything organized. So going back down here to this vector, 104 newtons east, what are our components of that vector? Well, the way we are expressing components is we would say that F1 is equal to the x component over the y component here. So the x component is just 104, and that's in the positive direction, and the y component is 0, because there's no part in the x direction. So if we wanted to break this down, we would call this the F1, the x component of x1, so we would do F1x like that, and this here would be F1y. It's the y component of the F1 force. Sorry, that F should look a little bit more like an F. There we go. So that's our first vector broken up into its 2 components, F1x and F1y. So let's do the same thing for the second vector. Second vector, F2, just goes straight down with a magnitude of 71 newtons. So breaking that into its vector, F2, we would just say that the x component of that is going to be obviously 0. And the y component, see how it's going down, that's a negative direction, so we would say it's negative 71. And this actually is in newtons. We can actually put the newtons outside the brackets like that. I forgot to do that in the first one there. So that's negative 71 is the y component there. So that's force 1 and force 2. Force 3 is a little bit more complicated. Now let's look at force vector 3, which is 122 newtons east, 15 degrees south. So this one, it's not obvious what the x and the y components are, so we're going to have to find them. So I always like to start with the x component. The x component is how far left or right it goes. So that's going to be the x component. And then the y component is going to be how up or down it goes. So x first and then y. Also, we know that the direction is east, 15 degrees south. So we start off by going east and then 15 degrees south. That tells us that this angle in here is our 15 degrees. So we need to break this up into its components before we can do any math with it, really. So how do we do that? Well, we need to find what that red arrow and that blue arrow are equal to. We can do that by just using our regular cosine and sine ratios, right? So if we call this F3x, it's the x component of F3, we know that we can find, or we can do cosine to find that, right? Because cosine is adjacent over hypotenuse. So we would write that as cosine of 15 degrees is going to be adjacent, which is F3x over 122. Or F3x is just going to be 122 cos 15. Which, if I do this on my calculator, 122 cos 15 comes out to 117.84 newtons. So that is our x component there. Our y component, on the other hand, F3y, instead of using cosine, we can just use sine. And in fact, once you get good at this, we can sort of just skip this first step where you're setting it up. And if you realize it's just the hypotenuse times cos or sine, depending on if it's the x or the y coordinate. So F3y is just going to be 122 sine 15 degrees. And I can just change that previous answer on my calculator to give me 31.58 newtons. So those are our 2 components. So if we express this final answer in the same form as the previous ones, we would say that F3 is equal to Well, the x component is to the right, so it's positive 117.84 newtons. And then the y component, remember, downwards is negative in the y direction, so we would say that the y component is negative 31.58. And these are both in newtons, so I can put that on the outside. There, we've broken down F3 into its x and its y components. Let's do the same for vector 4, and you can try this one yourself and then look at the answer. So I've already set up vector 4 for us. Now let's try to find what that x component is. So f4x, remember, which one is it, cosine or sine, that has to do with the x component here? Well, it's beside the angle, so it's the adjacent side, so we would say cosine. So it's going to be 157, the hypotenuse, times cosine of 60 degrees. And that, if we do that on a calculator, 157 cos 60 gives us 78.5. And then we could do the same thing for the y component. F4y is going to be 157, and it's the opposite side. Oops, I should fix that. No, 177. 157 sine 60, which is 135.97 newtons. Okay, and again, expressing this final answer in our matrix form, so F4 is going to be the x component. Again, let's think about positive or negative. We have to be careful about this. We have to remember this. Moving to the left, we defined as negative. So this would be negative 78. Oops. Negative 78.5. And then the y component is 1. It's going up, right? So it's positive 135.97. And these are both in newtons. There we go. By the way, one quick thing I like to do before I'm okay with this as my answer is I look at these two values and I see, do they make sense based on my sketch? This 60 degrees is pretty big, so it makes sense that my x component is smaller than my y component, which if you look at the numbers, it does come out to be. That's just a quick way to make sure you're not making any mistakes. And of course, double check that you've included the negatives in the correct spot. So now we're asked to find the total force acting on the box. So we basically just need to add up our 4 vectors. And now that we have them all in terms of the components, we can do that in the same way we've done previous questions. So we're going to add F1, which is 104 and 0. We're going to add to that F2, which is 0 and negative 71. We're going to add to that F3, which is 117.84. and negative 31.558. And lastly, plus negative 78.5 and 135.97. Okay? Remember what we do when we add vectors. We can just add all the x components together, and we have to add all the y components together to get our answer. Careful with those negative signs. We need to make sure we include them when we're doing it. So try it yourself, add up the x, add up the y, and I'll be right back with the answer. So here is the final vector. 143.34 is the x component and 33.39 is the y component. Notice how these are both positive numbers, so this means it's going to the right and up. Now this doesn't really answer the question because it wants the total force and the direction that box will move. So if these are the components of our final force, can we find that total force vector? Yes, we can. Just a little sketch. I know it's a little bit squished at the bottom of the page here, so if you need to find some extra space to do it, you can answer that there. So here we go. I'm using the edge of the page. I know you can't do that, but I'm cheating. So we say this x component here is 143.34 newtons. And the y component is positive, so it goes up. That's 33.39 newtons. So we want to know what this total force acting on the box is, the sum of those two. Obviously, so this is, I'm going to call this Ft for F total. And we can find that value just by easily using the Pythagorean theorem, right? So Ft, and actually this is the magnitude of Ft. It's the length of that line. It's just going to equal the square root of 33.39 squared plus, move that over a little bit, 143.34 squared. We get our answer for the magnitude as 147.18 newtons. And lastly, we need the direction. In order to express our final answer as a vector, we need the direction. So we need to know what that theta is. And if we've set it up always with our x first and then our y, our theta will always be from the horizontal, which is nice. We always use the same convention when we're doing it. So to find theta, we remember that we're going to use arctan, or tan inverse, of opposite over adjacent. In this case, opposite is 33.39, and adjacent is 143.34, and that gives us a value of 13.1 degrees. So if we want to express our final answer as a vector, we would say Ft, the total force acting on this box, is 147.18 newtons. And what direction is that? Well, if you look at the red line first, it's east and then 13.1 degrees north. East, 13.1 degrees north. So that's our final answer. Remember, once again, we like to take our final answer from the horizontal, from that red line, as opposed to from the vertical, just so we all have the same answer. There you go. That is adding vectors using the component method, just breaking it up into the components, and then adding the x, adding the y, and then finding the final vector. So in general, when we have a vector, call it vector A, we have our components ax and ay. The way we can find ax, it's always going to be the length of the vector, or the hypotenuse, so a times, or the magnitude of a, I should say, because it's the length of the vector, times the cosine of the angle from the horizontal. And similarly, if we're finding the y value, you can probably guess, it's just going to be the magnitude of a, or the length of a, times the sine of that angle. And that's what we did in the previous question, right? This is just the rule that always works. This only works, though, if you're going to take the theta from the horizontal. Okay, if it doesn't, you have to switch them around, basically. We can also express this in matrix form as just the x component and the y component. So it's the same thing. The magnitude of a times cos theta is the x component, and the magnitude of a times sine theta is the y component. That's just expressing the same thing in matrix form. So what I want you to do is pause the video here, try these next questions 1 and 2, and then unpause it, and I will show you what the answers are. Okay, so there was, first of all, a mistake with C there, so make sure you correct that. B and C were actually the same question. So I just changed C to being east and south just to make it a different question. One other thing to notice when we're answering this, notice how the first one we should be pretty okay with. It's just a direction to the east, or a vector to the east, that just looks like that. But question 2, F2, is a vector that is west and north. So it's going to look something like that. And notice how if we do our x component and our y component, the x component is going to be to the left, which is a negative direction. So I had to manually put in this negative sign here to accommodate that. The y direction was positive because it's going up. Same thing for the third one. So I just changed those two directions. So east and south is going to be going like that. So the x component is going to be positive to the right, and the y component is going to be down. So I had to manually put in that negative there. Okay? Try question 2 yourself now. So working with question 2, notice how I drew a quick sketch. Also notice how in my sketch, I didn't actually put in the negative 25 here. The down arrow accommodates that fact that we're going down, that is negative. So when we're finding our hypotenuse, we don't actually need to put in the negative there. It's just a length that's going in that direction. So notice how I found that F4, the magnitude, is 725 newtons, and the theta, the angle, is 68.2 degrees. So our final answer for F4 is 725 newtons, and the direction is going to be east and then 68.2 degrees to the south. There is our final answer. So I'm skipping to question 4 here from the homework. I've already drawn a little sketch, so Johnny driving 36 kilometers north, 30 degrees west. That's this first portion. And then 75 north, 10 degrees east. So he roughly goes sort of in the north direction both ways. So our final result is going to be sort of almost directly north. Probably not exactly directly north, but in that rough direction. It's nice to sketch it so you can see approximately what the answer is going to be. And we'll call that final displacement r as our resultant displacement. I also want to call these two vectors d1 as our displacement 1 and our d2, just so we can label them. Now, how we tackle a problem like this is we have to break down, we have to add those essentially. We have to add those two vectors, but it's not so easy because those vectors aren't in the components. We have to find the components of those vectors. So I like to break the question down like this. First vector, d1. So let me actually call that d1 there. d1, the angle is north 30 degrees west. So if you think about it, where that 30 degrees is, let me just zoom in here. That 30 degrees is going to be the 30 degrees from the vertical, right? Because it's north 30 degrees west. But when we draw our components, we like to draw our components with the x first and then the y. We should always do that. So if that's the case, you should be able to see that that angle inside is actually 60 degrees. So when we calculate, remember we should always calculate with the angle from the horizontal, we should take that 60 degrees. So anyways, let's zoom back out here. So let's find the components of d1. The x component, remember, it's the adjacent side, so it's going to use cosine, and it's in the negative direction because it's to the left. Actually, I should define the directions here. So we're going to say up is positive and right is positive. In that case, the red arrow there goes to the left, so it's going to be negative, and the length of that line is 36. I should actually do that here, 36 kilometers. I know it's a little bit tight on that little diagram. 36 cos 60 degrees. And the y component is going up, so it's going to be positive. It's just going to be 36 sine 60 degrees. So see, that's our d1 broken up into its x and its y component. And we could do the exact same thing for vector 2. So vector 2 looks something like that. It's 75 kilometers long. And the angle that it has, oops, that's supposed to be kilometers. The angle is north 10 degrees east. So again, zooming in just so you can see it a little bit better, the angle is from the north of 10 degrees. So if we want to find what this horizontal angle is for the x component, and here's the y component, the x component is going to be just 90 minus that, so it's going to be 80 degrees. So that's the angle we should use when we break it down into our components. So this components, for this vector, the x is in the positive direction, so it's just going to be 75 cos 80 degrees. And the y component is just going to be 75 sine 80 degrees. Notice how both of those are positive. Up and right are positive. There we go. Those are the only two vectors involved, and we've broken it up into its x components for each and its y components for each. Notice how I didn't actually plug those into my calculator yet to solve. And the reason is because when we find our final answer, we can just add those two things together as is, right? I can plug that whole thing into my calculator at once, negative 36 cos 60 plus 75 cos 80, so that I don't have any rounding errors by the end. Okay, so I'm going to do both of those in my calculator now, and you should do the same, and we'll see, we'll compare answers then, okay? So doing those, I get my final answer as negative 4.98 in the x direction, so 4.98 to the west, and then 105.04, so 105 kilometers north. And if we look at our initial sketch, that sort of makes sense, that we're going to go up by 105 kilometers and just a little bit to the west. The sketch actually wasn't so bad. But now, that's not our final answer. Those are the components of our final answer. We need to go back to find out what the actual length of that r is, and also what the angle is from the horizontal. So that's what we're going to do next. So I'm just going to zoom back in here. I'm going to draw a quick sketch of this this component. So we see that the x component is negative 4.98. So it's basically 4.98 in that direction. And then we have the vertical component, which is 105.04. Notice how this isn't exactly to scale. That's okay. And then our green arrow, right there, our resultant arrow, is there. So now we can use this triangle, and this is the angle we're going to find from the horizontal. We're going to use this triangle to find what our final answer is. So you can try that yourself, and then we can compare final answers. So I get my final answer, the result, what's it called? The magnitude of my final answer is 105.16, and the angle is 87.3. So our final answer at the end, R equals 105.16 kilometers. And if we look at our diagram there, it's west 87.3 degrees to the north. And that is our answer. So just taking a step back and looking at our whole process here. The first step was to draw a sketch of the situation, which just helped us see what was going on. Then we broke each vector up into its x and its y components, taking care of which parts were negative and which parts were positive. So in this case, just the x component was negative. Then we added those x components together to get a final answer for the x component of our answer, and we added the y components together to get the y component of our answer. So this was our final vector in matrix notation, but we needed to find the magnitude and direction because that's the question's asking for. So we draw this final triangle, find our magnitude and direction from that, and then write our final answer. You can see that this is done with 2 vectors here, but you could easily do the same thing with 3, 4, 5, 6, as many vectors as you want. Okay? There you go.